Right, okay, so welcome everyone. And in this lecture, we are continuing our journey to making correspondence, drawing correspondence between thermodynamics and statistical mechanics. So, what we did last time was to identify or postulate a correspondence between, or a fundamental correspondence between the entropy, as like thermodynamic entropy, with KB and the average of eta, which is the average surprise. Okay, and so what we looked at is in statistical mechanics, what that means that eta depends on the ensemble, and as a result, we need to check basically ensemble by ensemble what would be the properties of the entropy. Now, we looked at the macrocanonical ensemble last time, and I just want to mention that there was a sign mistake in the very last expression on the last video. It's just because I put this h to the dn at kind of at the very end, and I had forgotten that here there is to the dn and here there is minus, so it's basically h to the minus dn. Okay, now what matters is that the macrocanonical ensemble, basically S is proportional to the log of the number of states at energy in E and E plus delta E. Okay, so that's something you would find many times in different textbooks and so on when people try to explain what entropy is about. Right, so what we are going to do now is to look at the canonical ensemble part. And what we will find is that, yeah, we can provide an expression, and that's fine, but we can also use this to define some new quantities, some new correspondence, if you will. And that's what we are going to do here. So we still need to carry out this integral. I need to rewrite this down in terms of the actual probability density in the canonical ensemble. So ddri, ddpi, then exponential minus beta h, q and beta, then log, and then here I need to put this guy, hdn, exponential minus beta h, and then q and beta. Now, what I'm going to do is to express this log here, h to the dn exponential minus beta h, as follows. Okay, so I'm using the property that log of a times b is equal to log of a plus log of b. So this will be log of h to the dn over q and beta, and then here plus log of exponential minus beta h. Okay, now there are two things to notice. The first one is that this is independent of these variables. Okay, so essentially, it doesn't, like average of this, for example, doesn't do anything, or integration over this doesn't do anything, and this here is just minus beta h, right? Because the log of exponential of x is x itself. So in the end, we get the following outcome. So eta in the canonical ensemble, so let's put it this way, is equal to, so I will express it in terms of averages now. So that would be minus, minus the average of the log of h dn over q and beta. Okay, so that's the first bit, and then there is plus beta average of h. Okay, so now what I'm going to do is I'm doing one more thing in terms of identification, and this is something that I had put forward in the different analogies I had presented, is that this, I'm going to say that this is the same as U, the internal energy of the system. Okay, I'm saying the average energy is the same as the internal energy of the system. Okay, And after that, what I do is that I multiply everything by beta minus 1. So I end up with beta minus 1 eta beta is equal to minus beta minus 1. Then I've got, so I can put a plus and then put log of q n beta divided by h to the dn. And by the way, I can even remove this bit, right? Because since q does not depend on any of the random variables, then the average of a constant is just the constant itself. And then here I've got plus u, if you will, okay, which I literally identify to h, okay, so that's just how that's going to be. And then I'm going to reshuffle a little bit the terms. So I'm going to write that minus beta minus 1, then log of q n beta to the h divided by h to the dn is equal to u minus beta minus 1 eta beta. Okay, and now what I need to do is simply remind ourselves that eta is equal to s over kb. So it's equal to u minus beta minus 1 s over kb. Now this has an expression very similar to A, the Helmholtz free energy in thermodynamics. Okay, so I can put it here as well. So this thing here strongly resembles A, the Helmholtz free energy. Helmholtz free energy. Okay, and in fact, that's how I will define it. I can conclude, if this is something I accept, that I have that A. So again, I will put it as a conclusion, but that's something that follows, that A is actually equal to minus beta minus 1 log of q n beta over h to the dn. Okay, and I can also equally conclude that beta minus 1 over kb is equal to t. Okay, so these are two things that can be put together. So here I will get eventually this particular relationship, that beta is equal to 1 over kbt. Okay, so that's so let's put it in a different color here. Sorry, that beta is equal to 1 over kbt. Okay, and so this is basically what follows from our derivation. Okay, so we did manage to look at the entropy, and the entropy would look like this, and or like that if you want to calculate it explicitly. But then you can calculate the entropy simply by calculating first the free energy that is being identified as minus essentially kbt log of this quantity here, and then once you've done this, you calculate this quantity here, which is nothing but the average energy, and by subtracting the two, you actually get the entropy. Okay, so that's what we actually derived in this particular lecture, and in the next ones, we are going to try to find out some other thermodynamic quantities we can relate to.